Hello, hello, this is Jason Gonzalez. Today we're doing the 2022 AMC 12A problems, all of 1 through 25, and hopefully I'll separate them on the progress bar of this video, so you can click whichever one you want. I recommend you try the problem before looking at the solution. You can also just watch along. The problems are on artofproblemsolving.com, and let's get started. Alright, so let's get started with problem 1. So on these type of tests, it's very important to write very neatly, and you want to write everything very big. I think it's probably good to write everything on a separate page, so then it's easy to make sure you don't make mistakes and can check your work. So for this, I'm just going to write it out nice and big. And then this is just easy improper fractions, right? So we can just go through each of the steps. So first off, we get this is all what? This is 9 plus 1 is 10 over 3, so 3 over 10. And then we get, this is what? 3 times 10 is 30, 33 over 10, 10 over 33. And then finally, we get 3 times 33 is 99, plus 10 is 109. Obviously, I'm just multiplying the denominator by this and adding it to the numerator. And then we get 109 over 33. And that should be D. And let's make sure this is correct. And it is. How surprising. Right, now let us begin problem 2. So we have like the sum of 3 numbers, 96. We have one of the numbers in relation to third number. Basically, we have a bunch of relations between 3 numbers, right? So obviously, the easiest way to do this is just to do a system of equations with 3 numbers, x, y, z, right? So then we have x plus y plus z equals 96. Wow. And then we have the first number is equal to 6 times the third one. Amazing. Last but not least, we have third number is 40 less than the second number. And so now the easiest way that I see is just to plug things in, right? So first, let's plug this into here. We get x is equal to 6 times y minus 40, which is the same as 6y minus 240. Now, let's just plug, let's see, both these definitions into the x plus y plus z, right? So first, we have x is equal to 6y minus 240, and then we have z is equal to y minus 40. So we get, let's plug these in here, 6y minus 240 plus y minus 40 equals 96. Amazing, right? And now we can just simplify this all out. We get 8y minus 280 equals 96. 8y is equal to, it is good to be good at mental math for AMC. Unfortunately, I am not. 376, right? 376. And finally, we're going to divide. And we should get y is equal to, let's see, 8 is in 37, 4 times, and then 7. We should get 47. Now we have to get the rest, right? So now we have y, and now we can just plug that into this equation for x, right? Getting a little bit messy, but we get, well, 6 times 40 is 240, and so then the difference is 7 times 6 is 42, so we get x equals 42. I'm just going to like box those, and then obviously y minus x is equal to 5. That should give our answer to be E, and let's check if we're right. And if we look at the answer, it is E. Amazing, right? I know. Right, now we're moving on to problem 3. And last problem was a little bit messy. You should maybe try to write out your equations more linear and not like all over the page. But anyway, so in problem 3, we're given these rectangles, we're given their dimensions, and you have to figure out which one is the one in the middle. So then, for this type of problem, I would just start by looking at the outer thing you're told is, well, you need to make the dimensions match up, right? So, to do that, I would look at first which rectangle has the largest and smallest dimensions for a single side, right? So 2 times 7. 7 is the largest, and 1 by 6 is the largest. And I'm just going to take a wild guess. We want to pair up the 7 with 6 on one side. In particular, it's probably going to be this like top side. Hopefully you can see my cursor. Oh, I forgot to write problem 3. But anyway, so now, assuming we got those, now we need to make the bottom match up. And we're saying the side is 8. So how else do we get 8, right? Just spacing. Well, first off, let's try to get the other sides to match up. 2 plus what is equal to 6 plus what? Well, we need another big side, so let's say like 2 plus 6 is equal to 6 plus 2, right? We're going to guess the other sides, right? These bottom two are going to have like it's going to be a 6 by something, or something by 6 to match up with this. This is going to be something by, what? Well, we want something by 2, right? To match up with this. So let's see, what is our options for another 6? Let's say we have 6 by 5, right? We do not have anything used for that. And then for the other side, we can use the 2 by... So it's either 2 by 4 or 2 by 3. So remember, the other thing we have to make sure is that, lastly, we have these two add to 8. So we also need these two to add to 8. So we can see here that when we have the 3, which is one of our options, the 2 by 3 adds to 8. So with this all working together, we have the only thing that fits left in the middle is the 2 by 4, which is also answer, well, what is the answer? B. I guess you're just supposed to pick the one from the right that is 2 by 4. Anyway, let's check the answer. And wow, it is B. Amazing, right? I know, I'm so good at this. Okay, let's move on to problem 4. And so, for this problem, we are given two relations between n and other numbers based on LCM and GCD. Right? We have LCM of n18 is equal to 180, and we have GCD of n45 is equal to 15. So, let's just look at these relations one at a time. I think the easiest is GCD of n. N and 45. But GCD is the greatest factor both n and 45 have in common, which is 15. This means we can write n is equal to 15 times k, where k has to be relatively prime from 45, right? That means they can't have any factors in common. Now, let's look at the LCM. We know that both n and 18 must be able to be written in, like, n times x is equal to 180, and, of course, 18 times 10 is equal to 180. However, x and 10 must be relatively prime. So we have two relatively prime pairs, right? X and 10 and k and 45. So now, let's combine these two equations, right? And rewrite it as 15 times k times x is equal to 180. Or, simplifying, we have k times x is equal to 12. Now, we want to distribute the factors of 12, which we can write is 3 times 2 squared among k and x. So, let's look at 3. 3 cannot be in k, because 3 is a factor of 45. So that means x must have the 3 as a factor. Meanwhile, x and 10 must be relatively prime, but 2 is a factor of x, so that means, of 10, so that means the 2's must go into the k. That means k equals 4, and therefore we get that n is equal to 60. And that gives us the answer, 6 plus 0 is 6, which is B. So let's check that answer. And we should see that it is correct. And you can see a big thing for this problem, which you'll see is a recurring theme, is that we just want to write out all the information that we know and just look at relations one at a time until we finally arrive at the conclusion. Onward to problem 5, we see that we are given some sort of formula of distance. We want to know how many points are within that distance from the origin. So, and basically the distance from the origin, we can just say we want all points that have x plus y less than or equal to 20, right? And I think for these type of problems, it's best to just like think about it visually. So let's just draw like this big coordinate grid, right? And let's just draw what do all the points look like that have distance less than 20. Well, first, what are the ones of distance 0? It's just the origin. What are the ones of distance 1? It's these. What are the ones of distance 2? Right? It's just good to write out a few examples and see if you find a pattern. And now looking at the ones of distance 3, hopefully you'll be seeing a pattern of what they look like. They make these diamonds, right? And if you count how many points are on each of the diamonds, except for the center, each of them is a multiple of 4. We have, in the middle we have 1, and it's just 4, 8, 12, and the rest are all just multiples of 4. And you can think of it because, like, for every single time we go up from one diamond to the next, we're just adding one more point on each of the quadrants, which is why it's plus 4. So now we see we're doing this all the way up to the points of 4 times 20, right? And we want to get the sum of all of these. So let's just add the 1 separately, and now we're taking the sum of 4 times 1 plus 2 plus up to 20. And this is an arithmetic series. I'm not going to explain it, but basically you can just treat this as a formula as 1 plus 4 times 20 times 21 over 2, and simplifying this out, is equal to 1 plus, let's see, 4 times 10 times 21. So let's see, now we have 4 times 21 is 84 times 10 is 840, and then we get is equal to 841, and that is the answer, C. And let's make sure that's correct. And it is correct. Nice. Now in problem 6, we see that we are given a set of numbers, and we want to find, and we don't know one of the numbers. We want to find what it can be if the average of the set equals one of the numbers from the set, right? The set is 1, let's write it in numerical order, 1, 2, 5, 5, 7, and x. So, and we need the average to be equal to one of these numbers. So let's just, there's only 5 different numbers it could be, 1, 2, 5, 7, and x itself. So let's just iterate through all of them. So first off, let's take the sum. What is the sum of these numbers? 5 plus 5 is 10, plus 9, 20, right? So we know 20 plus x is equal to, divided by 6, needs to be equal to one of these numbers. So first off, let's try 1. Is that possible? Well, the key thing is that it says the data set consists of 6 positive integers, right? So let's imagine x was, well, let's say x was instead 4, right? So it's divisible by 6. 24 divided by 6 is 4, which we can see is bigger than 2 and 1, and that's the next largest number. After 20, that's divisible by 6. So it definitely cannot equal to 1 and 2, right? So let's just like cross those out. So now we have, what about 5? Well, to be equal to 5, x must be 5 5 times 6 is 30 minus 20. Must be 10, right? And that's perfectly possible. So x could be, let's just write x equals 10 is a possibility, because 10 plus 20 is 30 over 6 is 5. And what about 7? X can be 7, right? 7, let's see, the same thing, right? We can just do 42, which is 7 times 6 minus 20 is 22. If x equals 22, then we get the average is 7 just by plugging it in. But remember, we also have to be careful. What if 20 plus x divided by 6 is equal to x, right? Well, let's see if that's possible. If we rewrite this, right, we get that 6x minus x is 5x is equal to 20, which means that x is equal to 4 is a possibility. So then now we have these three possibilities that work. So that are the positive ones. So now let's just take the sum, which is 22, 26 plus 10. The sum is 36, which should be D. And let's check that that's right. It is indeed right. We'll now begin problem 7. So basically, we have a rectangle that's divided into different parts, and we want to color the different parts different colors. And we have like 5 different colors, right? 1, 2, 3, 4, 5. Yeah, 5 colors. However, we cannot have regions of the rectangle that touch be the same color, but otherwise we can reuse colors. So first off, I want to like abstract the problem as much as possible. In other words, get rid of the rectangle part, right? So I'm going to make it like a graph with nodes, basically. So here, you can see like this node will represent this rectangle right here, right? So let's just do that. So basically, we get a graph that looks like this, where the edges denote that the rectangle regions are like touching. So it looks like this, right? And now, basically, I told you we have 5 colors. Let's just start at a random vertex and then say how many options we have to color each of the other vertices. So first, let's say we start here, right? Also, I should have made this bigger, sorry. Let me do that. So then, let's say here, we have 5 options, right? We could just choose any color. Now, for this one, or actually, not yet. So for this one, now, we have 4 options, because we can't have it the same one as here, right? So now let's look at these. For this one, it cannot be the same as this or this, right? So we can have this one be 3 options, since and same with here. This one is 3 options, since it can't be the same as this one or this one. Finally, we have one left, and it cannot be the same as either of these, so it once again has 3 options. So we can see, now, we know the number of options. Right, we like just imagined for the first one, we picked an arbitrary color of our set, and then we said how many options we have for the rest of them. So now we can just multiply the number of options of each different region together, and we get, let's see, 27 times 20, which is equal to, what is this, 540, which is D. And let's make sure we're correct. And we are correct. Wow, I'm too good. And in general, this is a pretty common technique, where you just want to imagine how many options you have for each choice, and think about it one choice at a time. But now onto problem 8, where we're given some random expression filled with a lot of cube roots, and we want to, did I say problem 8, and we want to evaluate it. So for these type of problems, I think it's good to just rewrite it as exponents. Exponents are in general just easier to think about than the cube roots. So let's write it like that. Why can I write? Alright, 10 to the 1/3, right? So 1/3 is of course the same as cube root, times 10 to the 1/3 to the 1/3 times dot dot dot. First off, right, we know that when we raise to the power multiple times, this is the same as 1/3 times 1/3. So, and it will be the same, I'll write one more. 10 to the 1/3 to the 1/3 to the 1/3. Well, that's the same as just multiplying 1/3 times 1/3 times 1/3. So we can rewrite this as 10 to the 1/3 times 10 to the 1/3 times 1/3, which is 1/3 squared, times 10 to the 1/3 cubed, right? Etc. And also, now, when you write it like this, you can see you can just add exponents, right? Since you're, like, multiplying them. So then it becomes 10 times 1/3 plus 1/3 squared plus 1/3 cubed, dot, dot, dot. But then, this is just an arithmetic series, right? Or a geometric series. So then, if you don't already know, things that are in the form of a geometric series, where each term is the last one multiplied by the same constant, you can evaluate it with this formula. In this case, you take the first number in the sequence, which is 1/3, divided by 1 minus, and then the number that you multiply between each term, right? So to get from this one to this one, multiplied by 1/3, this one to this one, 1/3. So then if you evaluate this, you get, so 1/3 divided by 1 minus 1/3 is 2/3, so then 3/2 times that is equal to 1/2. So this is equal to 10 to the power of 1/2, which is equal to square root of 10, which is A. And let's make sure that is correct. And it is correct. Hooray. Sorry, you couldn't see the answer choices for that one, but here they are. Anyway, for problem 9, we're given a group of people where some of them are truth tellers, some of them are liars, and some of them are alternators, which means they alternate between truth and lie for every statement. So then now there are 3 questions asked, and whoever answers yes to each of the questions is given a candy. So let's just make a table like this, and corresponding to the types of people and whether they answer yes or no. And then let's see like what they answer. So then for the first one, do these ones answer yes? They do, right? Truth tellers will answer yes that they are truth tellers. They will answer no that they are alternators and liars, however, right? So then that's the answers. For here, they will answer yes since they're lying. They'll answer yes here since they're lying, and no here since they're lying. And finally, for the last one, now there are two types of alternators. There are those that start with true. There are those that start with false, right? So I'm going to make them two different groups, right? These one will go true, false, true. These ones will go false, true, false. Truth, false. Yeah, you get the point. So for the first one, are they a truth teller? If they answer truthfully first, they will give no. Are they going to lie the second one, right? And so if they lie, they're going to say no. And on this one, they're alternating. They're going to tell the truth, and they lie, so no. For the second one, they're lying. And are they a truth teller? They're going to lie. Now here they're going to tell the truth and say yes. And finally, here they are going to tell a lie, and say yes, right? So finally, we want to get the number of candy in total given to truth tellers, which is just only this box, right? So we know 22 in total answer yes to the first question, but we want to subtract out all of the liars from these, all the liars and alternators, which we can see are these two groups, right? So first, let's get how many are alternators. We can see just from our chart that's equal to, we can see to get the number of liars and alternators, that's just equal to the number from question 2, which is 15, right? So all you have to do is subtract 15, which is the total that answered yes to question 1. 22 is that, minus 15, which is the total that answered yes to question 2. That gives us only the ones here, which is what we want. 7, and that answer is A. Let's make sure that is correct. And it is. So you can see the key is just to write out all the information in a very neat and organized way, and then the answer should just come to you if you look at what everything means. On to problem 10. We can see that we want to make pairs of the numbers between 1 through 14, 7 pairs, so all of them must be in a pair. And then we have the condition that each pair, the smaller, the greater, is at least 2 times the larger one, right? So first off, I'm going to write 2 groups of numbers, and you'll quickly see right. So first, the ones up to 7, and then the ones up to 14 will be separate, right? 8, 10, 11, 12. Now, why did I write this in 2 separate groups? Well, you can pretty quickly see that in the ones over here, if any of them were the smaller number, then there's nothing that's in this group of 1 through 14 that could be the larger one, since 2 times 8 is 16, which is already larger than the largest in the group. So therefore, we know that all the ones on the left must be the smaller, and the ones on the right must be the larger. So now, let's just look at, for every single number, how many options do we have to pair it up? Let's just go from the largest to smallest. So for 7, right, you can only pair it with 14. Now, what about 6? You can pair it with everything less than 12. Now for 5, everything less than 10. And for 4, well, you can pair it with everything. Same with all of these. So we can see that the 7 is most restricted, right? And then the 6 is the next most restricted. So once again, like that earlier problem, let's just count one at a time how many options we have to pair each. So for the 7, like we said, we only have 1 option to pair. Now for the 6, we have 2 options to pair. Why not 3? Because we know the 7 is already taking away one of our options. So let's just kind of write it like this. So there's 2 options here. For the 5, we have 3 options, right? Since the 6 and the 7 are taking away 2 of them, but they can get 10, 11, or 13, or 6 was 13, 10, 11, and 12. And the 4 can take 1, 2, 3, 4 options, right? Same reasoning as before, but now the 4 takes 1. 3 only has 1, 2, 3 options, right? We take 1, the 2 has 2 options, and the 1 has 1 option. So now, so you can see, once again, we just looked one at a time from the most restrictive onward, since we wanted the ones that have like nothing preventing them from being making the choice first, which is why we went from 7 to 1. But now we can just multiply the choices for each number together to get the total number of pairing possibilities. So that's just, 1 through 4 is just 4 factorial, which is 24, times 3 factorial, which is these ones, which is equal to 6. And then multiplying that out, we get 24, 144, which is equal to E. And let's make sure that that is correct. It is correct. Now to problem 11, we are given that log 6 of x, the distance between log 6 of x and log 6 of 9 is equal to the distance between log 6 of 10 and 1 on the number line. So I think for this problem, it is easiest to just write it as an equation, where we think of distance as subtracting with absolute value, right? So log 6 of x minus log 6 of 9 is equal to log 6 of 10 minus 1. First, I'm going to rewrite the 1 as log 6 of 6, and you will see why. Because basically, if you know your logarithm rules, subtracting 2 logs with the same base is the same. It's just saying log 6 of dividing the 2 different things inside the log that's being subtracted. So x over 9, and don't forget the absolute value, you'll see that it's important, is equal to log 6 of 10 over 6. Now, with the absolute value, you always just want to think of absolute value as having two options. The inside is either positive or negative, and usually you just want to do those two options separate, which we'll do here. So first, if it's positive on the inside, you can just write it as normal, is equal to log 6 of 10 over 6. And since log is injective, we can just get rid of the log 6 then, and then we just have x over 9 is equal to 10 over 6. And that is the same as, let's see, we just do 9 times 10 over 6. This gives us the answer. What is 9 divided by 6? That's like 3 over 2. I'm sorry, 10 over 6 times 9. 3, 2 is 5. It's equal to 15. So we have x is equal to 15 is one of our possibilities. Now, what about when the inside instead is negative? Well, we know that negative log 6 of x over 9 is equal to, you can always bring factors of the log function as exponents of the inside. So we'll have log 6 of x over 9 to the negative 1, which is equal to log 6 of 9 over x is equal to log 6 of 10 over 6. Now once again, we can get rid of the logs and just solve the equation and get x is equal to 9 times 6 is 54 over 10, which is equal to, divide both by 2, 27 over 5. So now we have two options that x can be, right? Now, we want the product of all possible x. These are the only two possibilities, right? The only ever time we have multiple choices is with this absolute value function. So let's just do 27 over 5 times 15 is equal to 3 times 27, which is, let's see, 21 plus 6 is 81. And we can see that answer is E. And let's check the answer. And we do get E. Now, on to problem 12. We see that we finally have some geometry. Not my favorite, I'm sorry. And also 3D geometry. How disgusting. So we have regular tetrahedron, ABCD. So remember that a tetrahedron is the shape that looks like this. It's four sides where all of them are like equilateral triangles, right? Let's just label it A, B, C, D. And then we also have the midpoint of AB is M. What we're trying to find is the angle between CMD, right? So right here. So we can see that that angle is part of CMD, triangle CMD. So let's just get all the information about that triangle that we can. Now, it's easiest to just assign the side lengths a random value. Let's just say 1, right? They'll all be 1 because, you know, it's a regular tetrahedron. And it's easier to do that than saying x, like a random variable, and just say without loss of generality. But anyway, now, if the side lengths are 1, let's get the information about triangle CMD. And I'm just going to write it separately down here. MCD. So we have CD is equal to 1. Now what is, and we know that ABC is an equilateral triangle, like all the faces. So we know these angles are going to be 60 and 30, since ACM is half of ACB, and we see it's a 30, 60, 90 triangle. So this part is 1/2, this is 1/2, this is square root of 3 over 2. That is CM is square root of 3 over 2. We also know that we can do like basically the exact same thing to get MD is also square root of 3 over 2, right? AMD is 30, 60, 90 as well. So let's put this as square root of 3 over 2. And with all of the side lengths of triangle CMD, that should be enough information to get the angle that we desire. Now, there are multiple ways to finish off the problem. I'm going to use the law of cosines. So if you don't know, the law of cosines is just a random formula that says for a triangle that c squared is, you can see I labeled the sides ABC. It says c squared equals to a squared plus b squared minus 2ab cosine of angle C, where angle C means like the one opposite to length C, which is the one that we want, right? So let's just plug everything in. C squared, well, C is equal to 1, so that just 1 is equal to a squared plus b squared. That's just 2 times square root of 3 over 2 squared, which is just 3 over 4, minus 2 times a times b. That's just 2 times square root of 3 over 2 squared. Square root of 3 over 2 is 3 over 4 times 2 minus, let's just write 2 times 3 over 4 times cosine of the angle that we want. Cosine of angle, I'm going to label it M, since that's what it is in this triangle. So now, all we have to do is just solve for this value, which is exactly what we want, right? So let us just move, let's simplify this. 1 is equal to 3 over 2 times 1 minus cosine of angle M. And then we get 2/3. We get 1 minus 2/3 is equal to cosine of angle M, which is obviously the same as 1/3. So we should get the answer B. And let's make sure that is correct. And it is indeed correct. Now let's look at problem 13. So in this problem, we're given two complex numbers that have a set of values that they can be, and then we want to say, what is the area of all combinations of those numbers, z1 and z2, that they can be. So for these type of problems, I think it's usually best to look at what geometrically the values of the complex numbers can be. So I'm just going to write out a small graph, I guess. Let's see. So something like this, here's like the a plane, I guess. And and for z1, let's start with the z1. It says it can lie anywhere on the segment of 3, which is 1, 2, 3, and 4i. If we assume this is the imaginary axis, then it would be like this line, right? That wasn't very good. This line, no, this line. Okay, now for z2, it says anything with magnitude at most 1, right? So basically, it'll be anything in this circle is what z2 can be. Now we're adding both of them, right? So that means, let's think about adding z2 onto z1. z2 is anything here, and we can draw a circle around any point on that line, and that can be the range of where we can hit. We draw a bunch of circles, right? We see that in the end, we get a half circle off the end. Then we just get a whole rectangle here, and then a half circle. Let's see, that was not drawn super well. Let me erase the circles and redraw this figure. So we get a figure that looks like this. Now, let me just real quick redraw this down here. And we see that, well, let's think about the dimensions of this figure. First off, we have the length right here is from 3 to 4i, right? Well, we know this is a 3, 4, 5 triangle, so we know this length is 5. Now, what is this width? Well, we know it can be a radius 1 from either side, since we're adding z2, which has magnitude at most 1. So we can say here that there's 1 and 1. The radius of these half circles is 1. And you can see that combining these two half circles gives one circle. So basically, have a 2 by 5 rectangle plus a circle with radius 1. And obviously, that area then is going to be 2 times 5 is 10, plus pi times the radius 1 squared, or just pi. And that is closest to 13, right? That's around 10 plus 3, which is 13, which is A. And let's check that that is correct. Indeed, we get A. Now onto problem 14. We see we're given an expression with a bunch of logs. However, the annoying thing is that some of the logarithms are raised to a power, and logarithms are multiplied together. So we don't see that we can easily put everything inside of one logarithm. But we know that we must somehow cancel things out, since the answer choices are all without logs. But we see that the log is base 10, and all the things seem to be related to factors of 10, right? Like 5 and 20. So then we should try rewriting stuff to cancel as much out as possible. So then, after some trial and error, I may think of, well, 5 is 10 over 2, and 20 is 10 times 2. So that sounds like something can cancel out there, right? Usually when you have like plus something and minus something, things cancel out. So first, let's write that. 10 over 2 cubed plus log of 10 times 2 cubed plus, and then here we can just write these as exponents of 2 times log 2 to the negative 2, right? Now let's just use our exponent rules to expand this out. So remember that log of 10 divided by 2 is the same as log 10 minus log 2. Of course, log base 10 of 10 is 1, so I'm going to rewrite this as 1 minus log 2 cubed plus 1 plus log 2 cubed. And now we can bring the exponents as factors being multiplied by the logs, right? So we can take the 3 and negative 2 out. This is just minus 6 log 2. And this is looking pretty good, right? It looks like a lot of this will cancel out. So we have the plus and minus the same thing as we want. And let's think what will cancel out. We know you could just write out both of these completely. However, we know that all the terms where this part is raised to an odd power will cancel out with this part, right? Since the negative 1 will always stay negative for odd powers, but will stay positive for even powers. So this means we know that all the factors of log 2 and log 2 cubed will cancel out. So we only need to worry about the ones raised to the 0 and raised to the squared. So let's first do the 0. Obviously, we get 1 cubed from both of them, so we get 2, right? Get a 1 cubed here, like thinking about binomial expansion. And what about the term that's log 2 squared? Well, we know that one will have a factor of 3, and it will be positive on both of them. So here, we're getting 3 times log 2 squared, and also from here. So we get plus 6 times log 2 squared. Oh, sorry, and over here, I forgot to square the logs. But how nicely does that work out, right? Now we get these two cancel out, and we're just left with 2, which is C, which should be the answer. And let's look. And it is. I am amazing as always. Let's move to problem 15, and we see that in this one we're given a polynomial which has 3 roots, and they're supposed to correspond to the dimensions of a rectangular box. And then we want to find what if the dimensions of the box, all 3 of them, were increased by 2 units, then what's the new volume? So let's just think of it. I think it's pretty obvious that we're not going to be able to find the actual roots of this polynomial, or if we were, it would be quite annoying. So instead, let's remember Vietta's formula, which says that basically the product of the 3 roots, let's say for the original polynomial, is just going to be the constant divided by the term of the highest exponent. So here we have the product of the roots of the original polynomial is let me write out the polynomial, but the product of the roots is -6/10. Or it's the negative of that, right? So like imagine the polynomial looks like this. It looks like 10 times x minus a, x minus b, times x minus c, right? If a, b, and c are the roots, and we can see that the product of the roots will be a times b times c times 10 will be the constant term, be a times b times c, negative times 10. So the product of the original roots, a, b, c, is equal to 6/10. Now, if we increase all of the side lengths by 2 units, let's think about what that means for the roots. Basically, what it means is that, well, if before plugging in a worked, right, now we should have to plug in instead a plus 2. Or in other words, we should transform x to x minus 2, right? Because before a worked, now if you change x to x minus 2, and you plug in a plus 2, or b plus 2, or c plus 2, then we get back the original polynomial, and it will work out. So in other words, we want the polynomial that looks like this, has the roots of the new box with all the edges increased by 2 units. And finally, once again, all we care about is just the cubed coefficient and the constant coefficient. So let's find those. -6. So to find those, first off, the constant coefficient is not going to change, right? The only thing that's a cubed term is this 10 times x cubed. However, the constant coefficient will take a little bit more work. We have to get a constant from each of these terms. Here it will be -2 cubed times 10, which is -80, sorry. And then here we get 39 times -2 squared, which is 4 times -39. I'll figure that out later. Here we get 29 minus 2, and from the last one we still have the -6. And let's just evaluate what this is. This is -80 times 4 times 39. What is that? That's 36, 12, 156. 156 plus 80 is 100, 236, right? Then we have the 20, what is this, 29 times 2? You should probably have better handwriting than me. That is, 58? So that gets us to 294, and then 300, a nice number in the end, right? So basically all of this is 300. And then now we want to take, or sorry, it should be -300. We want to take the negative -300 divided by 10, and that will be the products of a plus 2 times b plus 2 plus c plus 2, which is equal to 30, and that should give us answer D. Let's make sure it is right. It is indeed correct. Now on to problem 16. Since we're on the final 10 problems, they'll probably start to get a bit harder. So for this one, we're given that a triangular number is the sum of the first n integers. Remember that this is just equal to the formula n times n plus 1 over 2. And basically, we want to find the fourth triangular number that is a perfect square. So in other words, we want n times n plus 1 over 2 to be equal to k squared. We're given like what the first 3 values of n are, and what is the fourth one. Or, we're given the first 3 squares, and we want the fourth value of this. So, one key thing about, what we want to do is just to analyze what needs to happen in order for this formula to be a perfect square. So one thing to realize is that because only one of n and n plus 1 are even, we can always split this formula into 2 ways. Either n over 2 and n plus 1 are integers, or n and n plus 1 over 2 are integers. And now, a key fact is that these are relatively prime. The reason is, imagine you let n over 2 be x, right? I'm going to show for this one, but it's the same idea for this. If n over 2 is x, then you can write this, n plus 1, as 2x plus 1, right? But assume that they're not relatively prime, so they have a factor in common. Then, that factor must also divide 2x plus 1 minus x, right? Because if it divides both of these, then it also must divide any combination of them. But this is just x plus 1, and it's well known that x and x plus 1 are always relatively prime. Therefore, we know that these two are always relatively prime. And same goes for this pair. Now, why does that matter? Well, we know that k squared, is we're looking for this to be a squared. But if we write these but since these are relatively prime, that means they can't have any factors in common. That means both of these must be squares. Alright, so in other words, we can write it as like this is x squared and this is y squared, over here like x squared and y squared. So now we know that either both of these are squares or both of these are squares. So why don't we just like try finding some squares and see if any of them fit these values. In particular, I'm going to try to find squares that work for either this or this, right? I won't go through working through them, but basically, if you like try a few different values, you'll see. Let's try the value 12 squared, which is equal to 144. Then, in that case, we have from 144, let's like multiply that by 2 and add 1. In other words, we're using this case. We're going to let this equal to n over 2, and then that leads to n plus 1 is equal to 144 times 2 plus 1, which is 289. What do you look at that? We got a pair of where this is 12 squared and this is 17 squared. So now we know that n is equal to 288 is a solution, and what we want is the sum of the digits of the, so we want the sum of the digits of k squared itself. We know that's equal to 12 squared times 17 squared, so now we just have to multiply that all out, right? So let us do that. 12 squared times 17 squared. Sorry, I'm losing my voice. But 12 squared is 144. Let's see, 144 times 289. Is there a fast way to do this? It seems like not. Well, for the sake of time, I'm going to cheat and just use the calculator. Well, on the test, you would just have to multiply this out. But this is equal to 41616. And just adding up the digits, you have 4 plus 1 plus 6 plus 1 plus 6. And this is equal to 12, 13, 14, 18. So we should get the answer is D. And let's see if that is correct. Indeed, we do get 18, D. Alright, nice. Now on to problem 17. We have this big equation with a bunch of signs, and we want to see when x is on the range 0 to pi, what is the set of real values of a that satisfy this equation twice. So there are two solutions on the interval for x, right? And usually the best way to get started is just to expand all of the sine of nx, right? Since otherwise it's hard to deal with those separately. So let's do that. On the right side we have a times sine of x. First expanding the sine of 2x, we just get 2 sine of x cos of x, right? And on the right side we get, well, what is sine of 3x? Well, we know sine of 3x is equal to sine of 2x plus x. So we can let's use our trig angle identities addition identity to do that, right? We know that's the same as sine of 2x cos of x plus sine of x cos of 2x. If you don't know this formula, just search trigonometric addition identities. And now we can expand the sine of 2x here is 2 sine of x, and then combined here is cosine x squared plus sine of x times, here we can expand this as 2 cos of x squared minus 1. And now we can group the sine of x cos x squared to get sine of x times, let's see, well, let's take out the sine, and then we get 4 cosine of x squared minus 1, right? So now we have this is equal to this. But here we see we can also cancel out all these signs, and now we're left with something a lot nicer. We have a times 1 plus 2 cos of x is equal to 4 cos of x squared minus 1. Oh yeah, also, if you want a general way to remember, like sine of nx or cosine of nx, I recommend you look up Chebyshev polynomials. This might be good to memorize. Just like look at the Wikipedia page, and you'll see like a generalized sort of recursive formula that will help you remember them. Anyway, dealing with this. Now, we can see that expanding this equation was good, because now everything is just in terms of cosine of x, which we can think of as one variable. I'm going to rewrite it as y. So a plus 2ay is equal to 4y squared minus 1. And rearranging, we basically have just a normal quadratic. 4y squared plus 2ay, minus 2ay, 4y squared minus 2ai, minus, no, plus, or how should I, minus 1 minus a, I'll just write it like this, is equal to 0. And since this is a quadratic equation, we can just use like the quadratic formula to solve for y. So we get y is equal to, what, negative b, which is 2a, plus or minus the square root of b squared, which is like 4a squared, minus 2ac, is 4 minus 4ac, is 4 times 4 is 16, 16 times 1, plus 16 times 1 plus a, and then all of that over 2a, which is 8, right? And now simplifying what's inside the square root, we get 2a plus or minus, well, let's see, this is the same as, we can take the 4 out, 2, and we get a squared plus 2 plus 4a plus 4. That's the same as, a plus 2 squared, all that over 2, or over 8. And of course, then this simplifies to 2a plus or minus 2 times a plus 2, all of that over 8. So now, let's simplify this out. So now we get two solutions, right? Let's just try out both the plus and the minus. We get a minus a over 2 is just a minus 1/2. And then the other solution is a plus a over 2 is 2a plus 2 over 4, which is equal to, let me just rewrite it as a plus 1 over 2. So we know that both of these need to be on the range of whatever cosine, remember y is the cosine of x, so they need to be on the range of, well, when x ranges to 0 to pi, cosine of x ranges from, let's see, ranges from -1 to 1, right? So we know that this works as one of the solution, so the other solution will always be this. So let's see, when is this equal to -1? Well, it's equal to -1. In other words, what p in the problem is when a is equal to, let's see, -3, right? So -5. Because -5 plus 1 is -4 over 2 is -3. -3 plus 1 is -2, divided by 2 is -1. Now, let's look at the right bound, or what r is. When is a plus 1 over 2 equal to 1? Well, that's when a is equal to 1. However, what is this q in the middle, where a is not a solution? Well, you need to think. There needs to be two distinct solutions, right? But what if what if -1/2 is equal to a plus 1 over 2? So it's like a repeating, right? Then there'd only be one solution. Well, when is this the case? In other words, when q is. This case is when we have -1 minus 1. This one, a is equal to -2, right? -2 plus 1 is -1, -1/2, yeah. So now we can just take the sum of p plus q plus r, which is -4, and should be a. And let's make sure that is correct. And it does seem to be correct. That was definitely a little bit more work than all the previous problems. Now on to problem 18. We are given this sort of a transformation on the coordinate plane, right? So you just rotate k degrees and then reflect it over the y-axis. And then you're just first doing that with 1 degree, then 2 degrees, then 3 degrees, etc. And you're saying if you keep doing that up to n degrees, when does the point 1, 0 return back to itself? And for this type of problem, I think the first thing is just to kind of draw out what the steps look like, and then maybe we'll see some sort of pattern or something to help us move forward. At the very least, we get a feel for it, right? So here's a plane, and let's just say this is the point 1, 0, and let's just do some of the transformations, right? So first, the first one is going 1 degree. This is the y-axis, x-axis. We'll just move 1 degree and then move across the y-axis, right? And this is what our first transformation looks like. Then we're going to move 2 degrees and go across the x-axis. And that is where our second operation ends, right? And then we're going to go 1, 2, 3 degrees and then go across the y-axis. And we end here. And if we keep going 4 degrees, we end here. And pretty immediately, we see an obvious pattern, right? So here's where it was after 0 operations, 1 operation, 2 operation, 3 operation, and 4 operation. So every time we seem to be going 1 degree this way, or every 2 operations, and over here we're going 1 degree this way every 2 operations, right? Well, I think it's pretty obvious that it looks like the first time when we're going to get back to here is going along this way and then reaching here. So what operation will that be? Well, we can see to move x degrees from -1, 0, it takes 2x minus 1 operations, right? And we want to move, just looking at the pattern. 1 degree takes 1 times 2 minus 1, 1 move. Moving 2 degrees takes 2 times 2 is 4, minus 1 is 3 moves. That seems to work, and if you keep drawing it out, or you could use induction to prove that this is for sure the case. So then we want 2x minus 1 degree. If we move x times, we'll go 2x minus 1 degrees, and we're going to go a total of 180. So now, is that what I meant to say? No, sorry. We want to move 180 degrees. So how many moves will that take? We're going to plug in 180 to get x to get, obviously, 359 moves, which should be answer A. Let's check if that's correct. And it appears to be right. On to problem 19. We have this sort of algorithm for picking cards, where basically we imagine going through the cards from left to right, and we first get the cards 1, 2, 3, etc. as high as you can go until you reach the end. Then you have to restart from the beginning, and you keep doing that in a sequential order of numbers until you get all the numbers, right? And it shows you an example here, and we want to know how many ways with 13 cards it will only take 2 passes to get all of the cards. So first, let's just think about what is the condition for this to happen. Well, basically, we know in our first pass we will get the numbers 1, 2, 3, 4 up to x, right? Then in our second pass, we need to get all of x plus 1, x plus 2, all the way up to 13 in the next pass, which means none of these two groups can be out of order, right? Both these groups must be in order. However, we can place them randomly among each other as long as the groups are in order within themselves. Well, this is also basically the same as, if you have your 13 cards, just going to draw a few of them, this is the same as if you have all your 13 cards, just choosing some of them that you're going to say. The ones in the first group are going to be the colored cards, and the ones in the second group are going to be the uncolored cards. Sounds reasonable. So then, however, there's a catch. What about the ways where it takes exactly one pass? Because we want to count the ways that take exactly 2 passes. If you color the cards like this, where some prefix is all colored, and then the ones afterwards are not, well, that's just the same as going 1, 2, 3, and then x plus 1, x plus 2, etc. Well, that's the same as that, it taking 1 pass. So we can say, basically, that we want to take all the possible colorings, where some of them are colored, minus the ones where a prefix of the cards are colored. Also, we want to take out the cases where either all of them are colored, or, sorry, we want to take out the case where none of them is colored, because that's also the same as taking 1 pass, right? So, well, let's think. How many ways are there for there to be exactly, how many ways are there to color a subset of the cards? So let's say those are the ones holding 1, 2, 3, etc. Well, there's exactly like a 2 to the power of 13 ways, which is the same as 8,192 ways to color the cards. However, we want to subtract out 8,192 minus, well, we want to subtract out every single prefix, which there's 13, minus none of them being colored, just 14. And if you do that, you get 8178, which is D. And let's check the answer. That is correct. And I thought this one was pretty easy. So you can see it's pretty important to make sure you look at even the higher number ones, because oftentimes the difficulty is out of order. Alright, now on to problem 20. We see another geometry problem, this time at least in 2D. And it is for this one's a little bit more complicated of a diagram than the previous, so it's more important for these later geometry problems to have a very good diagram. So let's just draw it out. We have a parallel trapezoid, isosceles trapezoid, ABCD, and it looks something like this. So here's an isosceles trapezoid. Let's see, let me rewrite that. It would look like this, and we know that the two parallel, let's see, what's the bigger side? The bigger side is AD, right? And now we know the smaller side is BC, and then we have, of course, AB is equal to CD, since it's isosceles. And then we also have this point, P, which I will draw, let's see, I will try drawing it here as a rough approximation, though definitely not to scale. It's better to try your best to make the diagram be to scale, but, you know, you gotta do what you gotta do. Anyway, it looks something like this, and here are the distances between P and all of the different points on the trapezoid. And then your goal is to find the ratio of BC to AD, right? So that's like this side length and this side length is what you want the ratio of. So let's try to find that. And with these type of geometry problems, usually you just want to do like 2 different things repeatedly. You just want to make like you want to add reasonable lines to the diagram, so then it can be like fit inside of or have nice shapes inside of it. And then you just want to write out everything that you know about the diagram, like write out any different new angles or side lengths or anything that you learn anything about, and assign lots of variables. So let's just do that. And with trapezoids, it's usually a good thing to just, especially isosceles trapezoids, but in general, it's nice to make it a triangle, right? So you're just like extending this top side to make it a triangle. And then I guess I will label this point Q. And then I'm also going to draw the line from P to Q. And this is just something that you wanted to be drawing some random lines to see if anything works out, basically. Or at least that's my perspective. Let me know if there's some more methodic way to do it. But anyway, let's label AB with the letter A. And obviously that's the same as this. Let's label this side length, B to Q, as B, and since it's isosceles, then this is an isosceles triangle, AQD. Let's just write that, AQD isosceles. How do you even spell isosceles? Alright, something like this. And now finally, let's label PQ as the, let's make it X, right? Nothing too fancy. And then, now the key thing for this problem is if you draw this pretty reasonable diagram, you now have all of these side lengths for triangles. Triangles P, DPQ, and APQ. So now for triangles DPQ, and a triangle APQ, it seems like you have the same sort of set of sides. And this is important because let me draw this sort of like general sort of diagram, right? So like something like this, have a triangle with a line in the middle, and then you have the sides B, C, C, B, A, and then this is side A, this is D, and this is M, N, and M. Now, one thing that you just have to memorize, it's pretty easy to derive with the law of cosines, but you want to recognize whenever you see a figure with these sides labeled that you can use something called Stewart's theorem, and it looks something like this. So the easiest way to remember is it takes the pairs C and C, B and B, so C and C, which is C squared N, plus B squared M is equal to, then you take the triplets, M A N, C and C, B and B, M A N, and lastly you take B A D, this pair, D squared. And like I said, this is just something you should have memorized and be able to apply whenever you recognize this diagram. And since we have this for both DPQ and APQ, let's just apply Stewart's theorem to both of them. So let's see, let's just make this a little bit smaller briefly. So let's say triangle DPQ. Right, so for Stewart's theorem, what do we get? For DPQ, well, just plugging in, making it look like the triangle I just wrote, we can do let's do four, what is that? It seems somehow, sorry about that, somehow it is drawing text. Anyway, we take, so the C squared N is the same as like, X squared A plus, X squared A plus, 4 squared B is equal to, let's see, A plus B plus, what is the last thing? We have 3A plus B, right? And remember, that's just like plugging in the sides of triangle DPQ into like this formula and then putting it into this equation. I'm going to do the same thing here with triangle AQD, APQ. Sorry, APQ. So then for this diagram, doing the exact same thing, we get, let's see, we get X squared A plus 1 squared B is equal to A plus B plus, let's see, I forgot a square, right? I forgot the squared here. And here it should be 2 squared A plus B, right? And immediately you can see that things are already working out quite nice. We have a lot of terms in common, right? Which means probably we can like eliminate a lot of variables if we just subtract the two terms. But real quick, I want to also further emphasize that remember what we're actually looking for, right? We're looking for the BC to AD, but realize that BC over AD, what is that equal to? Is there anything, you always want to look for like are there other like quotients that equal the same as what you're looking for, or just in general, or see if there's like similar triangles or something. And of course we have similar triangle, we have triangle let's do it, AQC is of course similar to triangle BQC, or this should be D, sorry, triangle BQC. And then this obviously means then that right, and that's because this is isosceles, so then, and like both these are parallel, so then it's pretty obvious that these angles are the same as these angles, right? And now we see that this side length BC to AD then must be equal to B over A plus B. And then, so we know that we want to get this term. But anyway, back to what we were doing here. Just write this down a little bit. Let's subtract these two terms, right? We're going to subtract these two equations and see what we get, since it looks like a lot of stuff will cancel out. Indeed, let's see, 4 squared minus 1 squared, that's like 15. 15b is equal to, we get these terms, so these terms cancel out, these terms cancel out. And for the other side, we get 3 squared minus 2 squared, which is 9 minus 4 is 5 times a plus b. And when you look at that, we just happen to get the exact terms we want, right? By rearranging, we can get b over a plus b is equal to 5 over 15, which is equal to 1/3. And that should give us answer B, right? And as you can see, you just want to draw out everything you can, write down variables for which side lengths look important, and see if you can apply any sort of theorems, or usually you can just get away with similar triangles, but sometimes you have to know some random formulas for the AMC. Oh yeah, we need to check if this is correct. It is correct, yay for me. And as far as knowing what sides you want to label and like how to extend the diagram, that's just something you have to sort of get better with intuition by practicing a bunch of problems. You should try the book EGMO. Now on to problem 21. We have this polynomial, x to the 22 plus x to the 1011 plus 1, and then we basically just want to find which of the answer choices is a factor of it. So first off, whenever you see like some random number, like 2022, like the year, sometimes it's good to just abstract that away using a variable. So I'm going to rewrite this as x to the 2y plus x to the y plus 1, where of course y is equal to 2022. And whenever you see this like exponents increasing by 1 at a time, like if you think of it as x to the y is a variable, then it's squared, then to the power 1, then to the power 0, you always want to think of like a difference of powers, basically. And in this case, you kind of want to write it like this. X to the 3y minus 1 over x to the y minus 1 is equal to our equation, right? X to the 2y plus x to the y plus 1. So then, and this is just a formula you should remember with the difference of powers. Anyway, with that in mind, we can see then that a factor of this equation will be a factor of this equation that is not a factor of this, probably. So then, now I'm just going to plug 3y back in to get x to the 3033 minus 1. Let's think, what are the factors of this? Well, using like a similar idea for the difference of powers, we know that factors of if let's say k is a factor of 3033, then we know that x to the k minus 1 is a factor for the same reasoning that we could do this, right? So let's just think, what are the factors of 3033? Of course, it's we have a 3, and then we also know that this is divisible by 3. And now I don't feel like writing out the rest of it, but there are no more factors of 3. Well, let me write out one more. This is 37, I believe. Maybe that's prime. Yeah, so it equals 3 squared times 337. And we know that 3. Why don't we just try plugging in some of the polynomials into here as k, right? Where k is a factor of 33. So let's try x to the 9 minus 1, since plugging in just 3 doesn't seem like it'll give any of the formulas, and plugging in 337 seems way too big. So x cubed minus x to the 9 minus 1. Well, of course, we can use like a difference of some sort of difference of powers on this, right? We can write it as like x cubed minus 1 times, right? I'm imagining a difference of cubes, where you're taking x cubed times x to the 6 plus x cubed plus 1. But would you look at that? This equation right here, that's exactly e. So then now we see that if x to the 9 minus 1 is a factor, that means this is e is a factor. So I'm going to say that's the answer, and let's just check. And it is correct. So you see, just whenever you recognize this, write it in this form, and then in this case, it was just seeing what the other factors are. Anyway, on to problem 22. We're given an equation such that the roots are two complex numbers, z1 and z2, and then we want to know, so the equation has a variable constant, which is c. We want to know for what value of c is the polygon made out of numbers z1, z2, 1 over z1, 1 over z2. Remember, they're complex numbers, so you put them in the complex plane. When that has maximum area, what is c closest to? So let's think about that. First off, one thing to remember is that because c it says is real, that means that the roots of this quadratic equation will be complex conjugates of each other, right? That's just a general thing. Whenever you have all real coefficients, you know that all complex roots will also have a complex conjugate as a root. So in other words, z1 is equal to z2, and then I'm just going to now just denote z1 as just a z. Now let's look at that in the complex plane. This means that in the complex plane, since z1 and z2 are conjugates, if z1 is like here, then z2 will be here. Now, another thing to remember is that for any complex variables, z times z conjugate is equal to the absolute value squared. You can just find that by writing out with the actual values of like a plus bi. But anyway, using this, we see that that 1 over z is equal to z over z squared. This means 1 over z1 should be somewhere over here, right? It'll be, because the conjugate is z2, and then divided by the absolute value. And then similarly, we have over here that 1 over z2 should be somewhere in here. And because they're reciprocals, of course, that means that z1 has the same absolute value as z2. Which means that now the quadrilateral that we want, which is here, is just made out of the triangle between the origin and z1 and z2, minus the triangle between the origin and 1 over z1 and 1 over z2. So we can just find the area of those two triangles separately, and then go about our way. But now, we still need more information, though. We do know that this is an isosceles triangle, but what are the constraints on like how big the sides can be? Well, this is where we use our quadratic equation. Using Vieta's formula, we know that the roots z1 times z2 is equal to 10, right? And since this is the same as just saying z times z, which is equal to z squared is equal to 10, that gives us that the absolute value of z is equal to the square root of 10. So we know that these side lengths right here, up to z1 and z2, must be 10. And similarly, then the side lengths up to 1 over z1 and 1 over z2 must be 1 over 10, right? 1 over 10. And now we want to find when is this area maximized? Well, since c is a real number, can be whatever we want, that doesn't add any other constraint. So then, let's think about when is this triangle's area maximized? If you don't know, you have a triangle with side lengths a, b, c, and like angle c. The area of the triangle can be expressed as 1/2 ab sine of angle c. And of course, this is maximized when angle c is 90, since that makes sine 1, so, and then that would make the area go to 1/2 ab. So let's apply that here, right? This tells us that the triangle must have angle 90 right here, which means, in other words, sort of like redrawing down here, we know that both z1 and z2 must be an angle of 45 off from the x-axis, since they're complex conjugates, right? So that and we also know that their length is square root of 10. So then this gives us z1. First off, z1, we now know that this is equal to, of course, this is a right angle, so this must also be 45. And then we get, this is just square root of 10 over square root of 2, where this length is square root of 5, this length is square root of 5, this length is square root of 5. So z1 is equal to square root of 5 plus I root 5, right? And z2 is equal to square root of 5 minus I root 5. Now, how do we get what c is? Once again, we use Vieta's formula. We know that c is equal to z1 plus z2, which you can pretty clearly see is just, in this case, 2 square roots of 5. But what is 2 square roots of 5? Well, the square root of 5 is approximately equal to 2.236. I think it's good to just have some of the small square root values approximations memorized. So then, of course, this is approximately equal to 4.5, or a, and then let's check if that's right. And it is correct. You can see in general, with complex numbers, it's good to just write them out on the plane, and then in this problem, you just want to think about what constraints the problem gives, so it simplifies it to a nice figure. And usually on the AMC, things simplify out to a relatively nice figure. Now on to problem 23. We have basically a harmonic sum, or sum of like 1 over integers, is equal to hn over kn, and we're wondering when the denominator kn is not equal to the least common multiple of the numbers from 1 to n, those numbers that we're adding the reciprocals of. Right, so let's think about that. And to do that, let's first think about, well, first we can rewrite it like this. And then let's think about the opposite. When will kn be equal to ln? 1 over I. So I'm wondering, when will it be equal to x over ln, where ln and x are relatively prime, right? Because of course in the simplified fraction, these should be relatively prime. Well, when that's the case, let's just rewrite this sum and assume that we already know the denominator is ln. Then what's the numerator going to be? Well, you can see if we divided this whole thing by ln, then we can also just multiply it by ln, and then it equals the same thing. Or in other words, we know that each of the I will be a factor of ln by definition, right? Since ln is the least common multiple of the numbers from I is equal to 1 to n. So we know the numerator will have to be equal to, this sum, because we know that this is an integer, and that this whole expression is equal to this, and And then if this is the denominator, we also know that the numerator must be relatively prime. Or in other words, we know that in this case, if we want the denominator to be equal to ln, then we should say the GCD of the top sum, ln over I, and ln should be equal to 1. But then we want this not to be the case, right? So then what we're looking for is the opposite. So we want the GCD to be greater than 1. So then that way, these won't be relatively prime, and you can divide out a factor, right? Like simplifying the fraction. So when will this happen? Well, whenever this happens, we know we need some factor then, of course, to be dividing both of these terms that's greater than 1. And since some factor will have to have some prime multiple as its factor, we can just say we want some prime that divides both. The sum of I is equal to 1 to n ln over I, and also we want that prime to divide ln, right? And of course that prime is going to be, the prime is going to be less than n. And we also know by definition that if this prime, less than or equal to n, and we also know by definition of the problem, if this prime is less than or equal to n, of course it's going to be a factor of the least common multiple, the numbers from 1 to n. So this one is a given. So the only term we really care about is this. We want to see, when is this the case? And we can rewrite this term another way, or rewrite it like this. The sum of I equals 1 to n of ln over I is congruent to 0 mod p, right? Just another way of rewriting it. Now we want to figure out, when will this be the case? Well, one thing that you may realize is that most of these terms are actually going to already be 0 mod p. When is that the case? Well, imagine ln, let's think of a specific example. Imagine one of the factors of ln is like p to the 10, but I is only equal to like x times p to the 5, right? Well then, of course, when you divide them, then it will still have a factor of p to the 5, and in other words, it will still be 0 mod p. And from this sort of example, you can see that the only terms that will be 0 mod p is when if p to the e, well, the only terms that will be non-zero mod p are going to be the terms where I contains the highest power of p that divides ln. We're rewriting this. We want p to the e to divide I, and p to the e to divide ln, but p to the e plus 1 to divide, to not divide ln, right? Because otherwise, if p to the e plus 1 divided ln, then we'd have p to the e plus 1 divided by p to the e, which would have equal p, and there'd still be a factor of p, and it'd still be 0 mod p. So we want to see for what pair. So now let's just start going over the actual values of p and see for what cases of n from 1 to 22. We'll find the non-zero terms mod p, and then we will see if those non-zero terms then add to 0 mod p. So let's get to that. First, for like p equals 2, oh yeah, there's one more thing I want to say. So then, first off, let's think in the general case. What are all the I that divide ln? Of course, what are all the I such that this holds? Well, of course, p to the e works, and also any multiple of p to the e works, right? Like 2 times p to the e, and 3 times p to the e, and all terms of like x times p to the e, right? Except we have to realize that x must be less than p. Why? Because if x is greater than or equal to p, then we also know that e will not be the highest power that divides ln, right? Because if we fix n, and we're saying all of these are the values of I that work, but then we also say x equals p has p times p to the e is less than n, then we know that p to the e plus 1 is less than n, and p to the e plus 1 divides ln, which is what we don't want, right? So we know that x has to be less than p, but otherwise all I of this form will work. And now let's actually start going over the values of p. So for p equals 2, we will have, what will we have? The only term that will work is just when x equals 1, so just the highest power that works. So we'll have ln over like 2 to the e is the only term, but this will always be the only term non-zero, always be congruent to 1 mod 2, right? So then basically, we know that no matter what the value of n is, this sum will always be 1 mod n. So we will never have the sum be congruent to 0 mod n. So we can't tell if the GCD will be greater than 1 based on p equals 2. Let's try p equals 3 instead, though. In this case, we'll have, well, once again, when there's only one term, let's imagine like from 3 to 5, right? There will only be one value of I that works, which is going to be 3. And no matter what, we know this term is non-zero mod 3. Why is the eraser not working? I'm not sure why that's happening. But anyway, we know this is non-zero mod p, mod 3. So then this will never work. However, what about the case from 6 to 8, right? We're saying this is n is equal to 6 to 8. In this case, I has two different values, such that the terms will be non-zero. You have ln over 3, once again, because 3 is still the highest power that divides any of 6 through 8. But also 6, which is 2 times 3, right? will once again cancel out all powers of 3, but it will also be non-zero. And you can see that this will always be equal to 0 mod 3. Why is that? Well, imagine that you have ln of x, ln over 6 equal to x. Then you're adding 2 times x, right? Ln over 3 is always 2 times ln over 6. But x plus 2 times x is equal to 3x, which is, of course, congruent to 0 mod p. And now we have one other similar case for p equals 3, and that is when n is equal to, in the range, this time we're going to have the highest power of p dividing n to be 3 squared, or 9. And whenever there are now, once again, 2 terms that are non-zero, in that case when both 9 and 2 times 9, 18, are within the range of 1 to n, and we'll see that both of these terms will be non-zero terms in our sum that we're looking at, the sum, ln of over 9 plus ln over 18, and this will, by the same logic as right here, be congruent to 0 mod 3. So now we have these two intervals, right, that of n that we can see. Based just on the prime 3, we can tell that these n will have this sum will have a common factor of 3 with ln. So in other words, this fraction will simplify, and ln will not be equal to k in the simplified fraction, since you'll divide it out the factor of 3. And you can keep going through this sort of steps with all of the different prime up to 22. Though you can stop pretty early, because it's pretty obvious that when there's only one term that divides, like when you get to higher powers of primes, and so then you can see right away that there's only one term, and so then the total sum will not be 0 mod p. But in the end, you'll see that these are the only two intervals of n that work. So we can say our answers are the values 6 through 8, union 18 through 22. So now to answer the question, we want to know for how many n was this the case where the fraction could simplify, so then the denominator is not ln, and we see, of the cases we got, we have 3 plus 5, which is equal to 8 cases, which should give us answer D. And let's check that answer. And D appears to be correct. That was definitely... Now on to problem 24. We want to create strings of length 5 using the digits 0 through 4, and we need our strings to satisfy a specific condition. We want at least one digit less than 1, at least 2 digits less than 2, and etc. In general, we want at least x digits less than x. And it doesn't matter where exactly these digits are in the string, we just need of all the digits in the string for them to satisfy that. Then we want to count the number of strings that work. So one way we can think about this is we need to have this sort of like checkbox of where all the conditions are satisfied. We need something less than 1, less than 2, less than 3, less than 4, less than 5, and we know that anything that satisfies here, we know that anything that is less than 1 will also satisfy being less than 2, right? So then, if our string is able to fill in all these checkboxes of having something less than 1, less than 2, less than 3, less than 4, less than 5, then it will be a working string. And let's use the example that we have in the problem, 0, 2, 2, 1, 4. If you go through this, we'll see that 0 satisfies being less than 1. So let's put that in that lowest checkbox that it works for, because we know then it satisfies all these constraints. And 2, we know that, well, this is like the lowest checkbox it fits in, since it satisfies all these constraints. However, for this 2, we already filled out this checkbox, and we know it doesn't work for anything lower, but it is also less than 4, so let's put it here, since it satisfies these 2 constraints, and we already filled out this one. Now, the 1 can fill out here, it's less than 2, it satisfies all of these, and then the 4, the 4 is less than 5, so we can just put it here. And hopefully, you see what I mean by when you have a string, you should be able to go through it and fill out these checkboxes where we want to put it in each digit in the lowest position possible, such that it satisfies the condition, since that will help us satisfy as many of the conditions as possible. And we, like with the 2, when the condition was already filled out, we just go up 1 more, since it also helps fill out that condition, and we just keep filling it out like that. But let's look at the non-working example in the problem. The 23404, right, in the statement, and let's try making the same sort of checkbox and see why it doesn't work. Well, if we fill out the same sort of checkbox, right, we see that, well, the 2 satisfies being less than 3 and helps all of these. The 3 satisfies being less than 4 and helps both of these. The 4 less than 5, and oh yeah, the less than 5 isn't in the problem, right, but we can just say that for consistency. Then what about the other less than? Well, let's first put the 0, which satisfies a less than 1, but the 4 only satisfies a less than 5, and if we keep going, we go off the page basically, right? We're off of the checkboxes, and we can see that anything that fills out this off of the checkbox sort of thing is useless. And whenever the useless bar is filled out, then we see that we're left with this open checkbox, and the string is not satisfied. So hopefully you see why this sort of checkbox idea shows that the string, when a string is satisfied or not satisfied based on if all of these values get filled out. Now, how does thinking about this sort of checkbox help us? Well, what you can see is that with this sort of checkbox, we basically have an algorithm where we imagine putting, for each digit, we're imagining putting a check in a specific position, but if it's already filled out, we keep moving forward until we find the first unfilled out thing, right? And this only works, and the condition is only satisfied if all the things are filled out, which is equivalent to saying the last one is not filled out. But now, in this case, you see there are always 5 checkboxes. So then, wouldn't it be nice to say, wouldn't it be nice to not have to have the case where like multiple checkboxes are off of the main 5 that we want to fill out? So then we can always say that the condition, whether the string is satisfied, is shown based on whether or not this single last checkbox is filled out. Well, we basically can do this if we imagine instead with these like lesson 1, lesson 2, lesson 3, lesson 4, lesson 5, and then like a dead checkbox. What we can say that if a string overflows more than once, right? So let's say the string 2, 3, 1, 2, 3, 4, 4. So we do this string, we fill out this checkbox, this checkbox, this checkbox, this checkbox, and this last 4. Sorry, no, I wanted 2, 3, 4, 4, 4. So we start this checkbox, this checkbox, this checkbox. Then this 4 would overflow to the dead box. Then for this one, what we'll do is instead of having another checkbox off the end, we're going to have it wrap around to the first checkbox. And so then now you can see we're always going to have only 6 slots, and 5 of them are filled out. And based on which one is not filled out, we can always tell whether the string will be good or not. And you might say, okay, so we made what was the point of that basically? Well, the point, and sort of like trying to simplify these conditions into these simple sort of algorithms, is that then if you are able to simplify the condition for counting something into a nice algorithm that's symmetric, as in this case, since it's circular, you can often find a helpful way that simplifies counting into a very simple equation, and you'll see what I mean here. Basically, in this case, what we have this algorithm where we select places to put them in, and they keep going circular if the place is already filled until we've like finished filling out 5 out of 6 spaces. But imagine the string doesn't work. Then we know we can make the string work if just for all the places we originally put them, we just added the difference between the empty space and the dead space, right? So in this case, if we just added to every single value, we added 1, 2, 3, 4 mod 6, since there are like 6 total spaces. In this case, we get the string 0, 1, 2, 2, 2. Right? Hopefully you see how I got this, right? The difference between the empty space and the dead space is 4, so I just added 4 mod 2 to all of these values to get a new string that does work. And then that will fill out the checkbox, the rotated case like this, which works. So basically, in other words, I'm saying for any string that doesn't work, there's a way to get a string that does work just by adding the same number to all of these, to all of the digits. So how does this help us count? Well, now let's also add in the digit of 5. So let's say maybe instead of dead, it's like a less than 6 case, which will also still specify as dead. In this case, now we have the algorithm. Well, all cases of the algorithm will be filled out now if we have each of the digits between 0 and 5, right? So that gives us 6 options for each digit. Right, so I'm imagining we're imagining that we can also make the digit 5 so that it's possible to start on this box. And the reasoning is that now we have like basically all cases of how the algorithm can go. Right, we're just like trying to make it as symmetric as possible. However, we can see, right, no matter what sequence of digits, 0 through 5, there's always a rotation, a single rotation. So like adding one number between 0 and 5 mod 6 to all the digits will always make a good string out of any string. So we can say out of all these combinations of numbers 0 through 5, we can say only 1/6 of them will be good. Hopefully that makes sense, what I'm doing. But when we do that, we get the value 6 to the power of 4 is the number of combinations, and if you evaluate that out, it should be 1296, which is equal to E. And then let's make sure that that is the correct answer. And that does appear to be the correct answer. On to the very last problem, problem 25. We're given a circle of radius r at position on the Cartesian plane, RR, and then we also have points that are on the x and y axis that are connected to form a line segment. And we want to say for for what case does a circle have 14 of those line segments connected to integers on the x and y axis? And then for whatever that case is, or the smallest case that is, then what is the ratio of the 14th largest, or the largest line segment divided by the smallest line segment that is tangent to the circle? So let me write that out and make that a little bit more clear. So we have like the x and y axis. Let's see x, y. And then we'll have a circle at r. It's r. Let me just draw some lines here. And then we'll have this big circle. And then finally, we're considering every single line segment that is at integer coordinates, like here and here, and is, let's see, pretend these are random integers. This would be bi, and this is ai. We see that it should be tangent to the circle, right? So of course that means there's a radius that intersects it. It's perpendicular to our line segment. And we want what is the case of r, that there are 14 different line segments, and then we're denoting their length, ci, and then we want to say what's the ratio of the largest to smallest length. So first off, let's just figure out when we fix r, what are all the possible lengths of that line segment. And to do that, let's write the length of the line segment in two different ways. It's a common thing in geometry that you just want to write some sort of segment or angle or something in two different ways, and then that will lead you to finding the solution. So in this case, of course, we can write it as ai squared plus bi squared, obviously. But what is another way we can rewrite this length, ci, right? So we're writing the length, or writing the length squared, rather. Well, the key thing is realizing that we know that this length right here, let's denote this b, this length is equal to right here. And then this length right here, well, let's note that a is also equal to this length, a. So we're saying that ci is equal to a plus b, but we're also then saying that a is equal to r minus ai, and b is equal to r minus bi. So then this is equal to 2r minus ai minus bi. And you might be asking, well, how did I know that these two line segments are equal, right? Let me just, no, I'll keep these. But let me redraw like a close-up, I guess, of this scenario. So we have a circle, and we have two, and basically what we have is two tangent line segments. Well, it will always be the case that these two segments are equal when two tangent line segments intersect. And this is just something you should probably remember, but hopefully it also makes sense, right? Basically we need to have equal angles between their intersection, since like these are both 90 degrees, and then we're like finding the intersection, and you can see that everything should be symmetric between this like sort of dividing line, I guess, for lack of better explanation. But anyway, so we can see the ci squared can also be written as 2r minus ai minus bi squared. But you might be wondering, wait, what if the tangent is instead of on this side of the circle, on the other side? So it looks something like this. Well, I'll leave it as an exercise for you, but basically you can make the same sort of argument that the distance here is equal to the distance here, and you end up with the exact same formula, this formula. And now let's just expand this formula and see what it simplifies to. So we have bi squared plus bi squared is equal to, so this side, let's just take all the squares of the individual terms. Have 4r squared plus ai squared plus bi squared. Of course, these are all going to cancel out. And then let's take the multiples of two terms, right? So we have like every combination of two terms will have like 2 times in the sum. So we'll have plus 4rai plus 4rbi plus, no, these should be minus, right? Sorry, that is my bad. This should be minus plus 2aibi. And let's just rewrite this all more neatly. So I'm going to rewrite this as 0 equals 4r squared minus 4rai minus 4rbi plus 2aibi. And one could hope, and we'll see this is the case, that you can factor this, so then it gets into a nice Diophantine equation, where you can just iterate over some sort of simple values. And to see that, we can rewrite this as, let's see, how are we going to factorize this? Well, we know that we want, first let's divide everything by 2, right? Of course we can do that. So just divide all these by 2, and now we know we want the ai and bi to multiply, and we also are multiplying this with 2 rai on both sides, right? I mean 2r. So you can see that when I factor this, right, basically what I'm doing is I'm looking at this term and trying to force it to factor. So the a and b should be in separate terms, and we see we also have these terms, right? So then the 2r is always multiplied by an a, which means we need a minus 2r, the opposite side. But then finally, we get this expression gives us an extra 4r squared. So in order to balance the equation, we need to add 2r squared to this side, right? Hopefully that makes sense. Basically, we're just factoring this equation, and it becomes this new, nicer equation. And this equation looks nice because now it seems that since this side is an integer, we can think of it as taking two factors of whatever integer this is, and then denoting each of these two terms to be one of the two factors, and which is a very common technique on the AMC. So let's do exactly that. We know we need 14 solutions, so we might have to guess a few different values of r, of what we think that will be. However, we can think that the value, with a little bit of trial and error, you'll see that the value r equals 6 seems the most promising, which let's write that in factored form. So if r is equal to 6, that will lead to, let's see, if r is equal to 6, we'll get the term 2 cubed times 3 squared on the right. Now, why is that promising? Well, we know based on like the exponents that we have 12 factors on this side, which is just slightly less than 14. However, we also can consider negative factors, and this looks like it will be around the ballpark of having the correct number of solutions. So let's just think about what is the smallest and largest solution for, and remember that CI, we're looking for CI, right, which is equal to 2r minus ai minus bi, we said above. So if we want the smallest solution, we should minimize the sum. And if we want the largest solution, we should be maximizing this. And if we want the largest solution, we should be minimizing the sum of ai and bi. So let's think about how to do that. If we're trying to minimize the sum to get the largest CI, we probably want a relatively equal distribution of 12, so like 3 and 4. That's my alarm. Anyway, so let's say these are 3 and 4. I guess I should. In that case, we want the values. What do we want? We also know that we already know that 2r is equal to what? 2r is equal to 12 because we said r is equal to 6 is what we're trying out. So we'll have this expression. So if we want this to be 3, right? Because remember, we're like splitting up the factors of the... Did I do this right? I did not do this right. It should not be 12. This should be 24. 2 cubes is 8. 8 times... No, this should be 72. I don't know what I'm saying. So we went 8 and 9, right? Sorry, that is my bad. So we went 8 and 9. I don't know why I was saying that. But anyway, if we have this be 8, then we can see that AI should be equal to... AI should be equal to, what? 8 plus 12, which is 20. And BI is equal to 9 plus 12, which is what? 21, right? Now let's think about this opposite case when we have the factors negative 8 and negative 9, right? Because of course these factors will also multiply to 72. In this case, we will have A be equal to what? We will have it equal to negative 8 plus 12 is 4, and BI is equal to 3. And you could check some other values, but it's pretty clear that when you're trying to optimize something with the multiplication expression, you usually want either the values that are closest together or farthest apart, and you can get that intuition from calculus or just like experience. I don't know. But anyway, if you try other values, you'll see that this gives the largest sum of AI plus BI, this gives the smallest sum of AI plus BI. If you do a little bit of casework, you'll see that there are indeed only 14 different pairs of AI and BI that work. So now, if you believe me on all that, you will see that this is indeed the solution that is desired. So let's just plug in for the two different values of CI, right? So, oh yeah, remember how I said this is the value of CI? That's the case when it's down here, but when the case is up here, CI will instead equal to AI plus BI minus 2R. Sorry. So then, for the first case, using these values, we'll have 12 minus 4 minus 3, which is equal to 5, is one of our values of CI. The other case is 20 plus 21 minus 12, which is equal to 41, 31, 20, 29, equal to CI. So now, taking, did I do this right? Oh wait, no, I'm forgetting. I just said, for the other case, I guess we should be looking for the most extreme values. So what about like 1 and, what about, let's see, 1 and 72, right? In this case, we will have AI is equal to, what? 1 plus 12 is 13. And then BI is equal to, what? 72 plus 12, which is equal to 84. Sorry. So then, what we should be using is not this case, but these two cases are the ones that are the most extreme. So then, what we want to do is take 13 plus 84 minus 12, which is equal to 85, as our largest value of CI. Sorry, you can see that another thing is that if your answer choice is like not listed, then it's probably wrong. So that's like one way you can check. Anyway, now we can do it. We see that this is C14, and this is equal to C1. So C14 over C1 is equal to 85 divided by 5, which is equal to, it seems to be 21. 21. Is that right? That's not right. 5. No, what is it? It's 17. Sorry. I don't know why I cannot do division. Anyway, we see that 17 should be the answer, and that is E. And that is one of our answer choices. So let's check that it is correct. And we see that 17 is correct. So that appears we have solved the final problem in this set. That is the end of my AMC 2022 12A tutorial. As you can see, the general strategies that you just always want to follow are just write out all the information you know, look for symmetries, think about what formulas seem relevant to the situation at hand, and then hope for the best, I guess. And don't forget that sometimes you need to do a little bit of casework to finish up a problem. But hopefully my explanations were not too terrible for all these problems. This took quite a while to make, so make sure you subscribe and let me know what sort of contest you would like me to go over next. But that's all for now, so adios. Also, OR's code Tiger for better results.